And if you are not able to evaluate a property of your system, you cannot solve any problem in thermodynamics. So today's lecture determines, whether you can be successful or not, throughout this semester. That motivates you, right? No? Okay. So last Tuesday, we studied there are 5 phase change processes, and for each process there is a way to evaluate a property. You cannot. There's only one. There is no one. Straight. The solution to evaluate property. So depending on the phase change process, you have to use a different way to evaluate the property. So that means that the evaluating a property of a phase change material, has 2 steps. The first one is determine what phase change process your system exists as. So you need to be able to determine the phase change process. And once you determine that, then you go to appropriate table for that phase change process. Then you will be able to, determine property. Okay. So today we are going to talk about how we can evaluate, how we can determine the phase change process when you have a phase change material. And we will go over a few problems, a few examples, so you can understand, how to, determine the phase change process. Then the other half of today, we are going to talk about, the instructions, how we evaluate a property when the phase change process is this one. Okay. So we are going to, to go over everything today. So we all know that there are 5 phase change processes, and to determine the phase change process, the easiest way is to use a property diagram. So we are going to talk about property diagram first, and we will learn how to make a property diagram, and we will go over a few problems. So there are 2 property diagrams we can use. One is PV diagram if you know a pressure. So if you do not know any property of your system, you cannot evaluate a property. You need to know some minimum information. Let's say this is the pressure of the system. What is the temperature? Or this is the temperature of the system, and this is the specific volume. What is pressure? So you need to know at least 2 property values to evaluate another property. And to start, you need to know at least either pressure or temperature. By the way, we will know, that there are 5 phase change processes: a compressed liquid, saturated liquid, saturated mixture, vapor, and superheated vapor. So if you know pressure, and you can make PV diagram. So let's say, the pressure is 100 kilopascal. Then PV diagram looks like this. So this means when you have water, by the way, this is for water, okay? So assuming that, that our system is water. So when you have water system and you measure the pressure of the water system, the pressure is 100 kilopascal, then your water should be somewhere on this line. If here, that means the pressure is not 100 kilopascal. If you are here, then the pressure is not 100 kilopascal. As long as the pressure of the system is 100 kilopascal, that should be on this line. 300, that we are going to talk about that, but if pressure is greater than 100 kilopascal, this graph moves upward. So 300 means that, that there is another curve like that. 500 means that on top of it. If the pressure is less than 100, then the graph is going to be moved downward. Similar, the shape. This way, this way, this way. So this one, this particular, the lines is for 100 kilopascal. So if you have less than 100, this graph moves downward. If you have a greater pressure than this one, this graph moves upward. But we are going to talk about that. But let's talk about this particular pressure. And to complete this TV diagram, this one is called TV diagram. The vertical axis is temperature. The horizontal axis is specific volume V. So TV diagram, not the television, okay? So to make this TV diagram, we need to know three property values. One is the temperature of this horizontal line, that is saturation pressure. T set. You remember what is T set? Saturation pressure and saturation temperature means the boiling temperature of water at this pressure. And we need two more properties, that is this one, Vf, and this one, Vg. So let me explain, how this, the graph works. First, if you want to boil water, then the water is at room temperature. So the temperature is low somewhere here. If you heat this water, its temperature goes up and its volume goes up. So this way, that is compressed liquid, a substance that it is not about to vaporize, like a water at room temperature. But if you heat this water, we don't expect, that it boils right away. Its temperature goes up first, right? So that is compressed liquid. And then, once the temperature reaches its boiling temperature, that is T set, this point is saturated liquid, or liquid that is about to vaporize, because the temperature is already the boiling temperature, T set. And if you keep heating the system, the temperature of the system is not going to increase anymore, because this is the saturation temperature. So instead of increasing temperature, it's going to change its phase from liquid to vapor at a constant temperature. So liquid molecules become vapor molecule. That is saturated mixture. More and more liquid molecules become vapor. And there will be one moment, every molecule in the system is in the vapor phase, which means that, the boiling is complete. That is saturated vapor, this point. And there is no more phase change can occur because everything is in the vapor. So any heat to the system is going to increase the temperature, superheated vapor. So on this TV diagram, this line represents number one, compressed liquid. This point represents number two, saturated liquid. This horizontal line represents saturated mixture. Number four, this point is saturated vapor. And this line represents superheated vapor. So T set is the temperature of this phase change, saturation temperature, boiling temperature. Vf is the specific volume of saturated liquid. Vg is the specific volume of saturated vapor. So this F represents, this subscript F represents saturated liquid, that is F. This G represents saturated vapor, that is G. So V is the specific volume, Vf is the specific volume of saturated liquid, Vg is the specific volume of saturated vapor. So that's how we make TV diagram. There's another way to have a phase change. That is when you have a constant temperature. If you know the temperature of your system, let's say 30 degrees Celsius, then you can make another property diagram. In this case, not PV, it's going to be PV, pressure and volume diagram. This PV diagram looks similar to TV diagram, but it is upside down. So not this way, it is going to be this way. So PV diagram looks like this. And there are three properties that you need to know to complete this PV diagram. They are similar to this one. Not T set, it's going to be P set. This one is the same, VF. This one is VG. So from our, the own experience, to have a phase change, we need to heat something, right? If you want to change the phase of water from liquid to vapor, what you can do? You can heat it, right? At constant pressure. If you heat water in your house, the pressure inside your house is going to be constant pressure. So in that case, the water behaves on this line. That's a phase change. But that's one way. That's not the only way. That's one way. Another way to have a phase change without changing temperature is decreasing pressure. So instead of increasing temperature, you can decrease the pressure of the system and then have phase change. So initially, you can say maybe 30 degrees Celsius and 100 kilopascal like water. And if you decrease the pressure of the system, then at a certain point, when pressure is the saturation pressure at this temperature, it will undergo phase change and it becomes vapor, which is uncommon in our real life because our real life is more like constant pressure process. Unless you go to on top of Mountain Everest or dive into the water 100 meters. In real life, it's more like constant pressure process. But thermodynamically, this phase change is nothing different from this phase change. So there are two different ways to undergo phase change. One is increasing temperature, the other one is decreasing pressure. Okay? Then, on this PV diagram, we also have these 5 phase change processes. First, this line represents compressed liquid, number 1. This point represents saturated liquid. This line represents saturated mixture. This point represents saturated vapor. And finally, this line represents superheated vapor. So you need to understand these two diagrams. Because if you know pressure of your system, this is the diagram that you are going to use. But if you do not know pressure, but temperature, if you only know the temperature of your system, this is the diagram that you have to use. It's not, the thing that you can select. It depends on the information you have for your system. Okay? So you should be able to make both diagrams. Okay? Of course, we will, solve a few examples later so you can practice together. Okay? Then you may remember, that there are other properties, than temperature, pressure, volume. What about internal energy, U? What about enthalpy, H? You haven't studied enthalpy, H yet. You will study 10 minutes from now. So what about if you're not interested in V? If you are interested in, let's say, specific internal energy, U, then can we make another property diagram for specific internal energy U? Yes, you can. So there are, the 4 properties that you can make. One is V, the other one is specific internal energy U, specific enthalpy H, and specific entropy S. But this entropy S we are going to study later in chapter 6. So until then, just V, U, H. So what about, I'm not interested in specific volume. What about if I want to determine this U? Then can we make a property diagram for this U? Yes, you can. How? Instead of TV, you can just say, I'm going to make TU diagram. Can we do that? Yes, you can. Then, does it look different from this one? No, they look very similar. So if you make TU diagram, it's going to be T. He said is the same. Instead of VF, VG, you can say UF, UG. Then the horizontal axis is going to be specific internal energy. The graph looks similar. What about on this line, on this PV diagram? Can we make PU diagram? Yes. Instead of PV, you can say PU. Then it's going to be UF, UG. What about enthalpy H? I want to determine H. Then can we make TH diagram? Yes, no problem. Instead of UF, UG, you can say HF, HG. For PU diagram, you can say PH diagram, and this one is going to be HF, HG. So V, U, H, they are interchangeable. Entropy that you will study later in chapter 6, not now. It's a little bit complicated, so you need to understand chapter 3, 4, 5 to be ready to study entropy. Then, so that's everything about, how to make T temperature diagram and pressure diagram. Now let's talk about what about if the pressure is greater than this one? The answer to your previous question. If the pressure goes up, this graph moves upward. If the pressure goes down, this graph moves downwards. So this means when pressure of your water is at 100 kilopascal, to be 100 kilopascal, water should be here. So if you have a compressed liquid at 100 kilopascal, that water should be on this line. If you have a saturated liquid at 100 kilopascal, that should be on this line. And super vapor on this line. But what about pressure is not 100, but 200? If the pressure is 200 kilopascal, 200 kilopascal, the graph is going to be this way. What about if the pressure is less than this value? Let's say 50. If the pressure is only 50 kilopascal, then the graph is below here. 50, 60, 70, 40, 30, etc. Okay? Huh? No, you can use different units. It can be bar, kilopascal, ATM, anything you can use, but you want to stick to one unit, not to confuse, right? And I recommend use the kilopascal, which is the most common pressure unit that we study in thermodynamics. What about this PV diagram? If the temperature goes up, the graph moves upward. This one is for, let's say, 100. If temperature goes down, the graph moves downward. This one is for maybe 10 degrees Celsius. Now, this is what? This point, saturated liquid. This one is saturated liquid. This one is saturated liquid, right? So you can connect them. What about here? Saturated vapor, saturated vapor, saturated vapor, number 4. You can connect them. Then the graph looks like this. This is called saturation curve. And the top of this saturation curve is called critical point. Above this point, there's no more liquid water. You only have supercritical water. Okay? So that's everything about how to make PV and PV diagram, or PU, PH. Then let's see how we can use these phase diagrams to determine the phase change process from 1 to 5. So let me give you an example. Let's say, that I have a water system and I wasn't able to measure the pressure of this water. Let's say the pressure is 200 kilopascal. And the temperature was 150 degrees Celsius. Now, can you determine the phase change process? Yes, we can. Then how? By making a property diagram. So I'm going to use this 200 kilopascal to make a property diagram. So the pressure of this water system is 200 kilopascal. That means this water should be on this TV diagram. At 200 kilopascal, TV diagram looks like this. And by the way, let's complete this TV diagram first. And if you want to make this TV diagram, we need to find 3 properties. They are T set, Vf, and Vg. Then where can we find T set, Vf, Vg? What is the property that we know? 200 kilopascal. So you can go to saturated water pressure table. That is table A3. This is table A3. If you read this title, properties of saturated water pressure table, then let me explain how to read this table. This is the pressure that you know, and any numbers to the right is the properties that you can use to make the property diagram. So what is the pressure? 200 kilopascal. So let's find 200 kilopascal. The first column is pressure. So where is 200? Oh, these numbers look pretty small. Why is that? Let's look at the unit. What is the unit of the pressure? Bar. 1 bar is 100 kilopascal. So 200 kilopascal is 2 bar, which is right here. So this is 2 bar. Let me zoom in. So this is the input. At 200 kilopascal, which is 2 bar, the second column is temperature. This is T set. The saturation temperature is going to be 120.2. And this is Vf, 1.0605. By the way, specific volume of saturated liquid is usually very small. So the numbers are too small. So we multiply this Vf by 1000 and wrote them here. So this value, 1.0605 at 200 kilopascal, the specific volume is actually this number divided by 1000. Cubic meters per kilogram. What about Vg? So this one is Vf. There's a Vg. So at 200 kilopascal, this one is T set, Vf, Vg. So let me write these 3 values on this TV diagram. So T set first, 120.2. T set. This one is 120.2 degrees Celsius. What about Vf? 1.0605 divided by 1000. 1.0605 times 10 to minus 3 cubic meters per kilogram. What about Vg? 0.8857 cubic meters per kilogram. So we are almost ready, to use this TV diagram. Now let's, find where is number 1, where is number 2, 3, 4, 5, the phase change processes. On this TV diagram, this line represents number 1, compressed liquid. This point represents number 2, saturated liquid. This line represents number 3, saturated mixture. This point represents saturated vapor, number 4. And finally, this line represents number 5, superheated vapor. So now we completed this TV diagram by using this pressure. So as long as the water has 200 kilopascal pressure, that water should be on this line. Now we have one more clue to locate our system. What is that? The temperature of our system. So let's find this temperature on this TV diagram. Where is temperature on this diagram? This vertical axis. So where is 150? How do we know? Oh, we know this reference point. He said is only 120. So 150 should be up here. So what is the phase change process? Number 5, superheat vapor. So that's how you determine the phase change process. 150, this point. Number 5. So you can say, according to this TV diagram, we have superheat vapor. Any question? Then let's talk about something else. Okay, one problem is not enough. So let's practice one more problem. Now we have water again. Knowing pressure is too simple. So let's say I know temperature this time. When I measure the temperature of the system, it was 70 degrees Celsius. And what else? I measured the specific internal energy, U. It was 500 kilojoule per kilogram. Now, this one looks a little more complicated than the other one, right? Not necessarily, they're actually the same problem. Specific internal energy, the total energy that you studied in chapter 2. U plus kinetic energy plus potential energy, that U. So we want to determine the phase change process of this water system. What you need to do first, make a property diagram. Then what kind of property diagram can we use? It's going to be either temperature diagram or pressure diagram. If you know pressure, it's going to be temperature diagram. If you know temperature, it's going to be pressure diagram. Then what do we know? We know temperature, so it's going to be pressure diagram. P something diagram at 70 degrees Celsius. And this horizontal axis can be V, U, H, S. Which one do you want to use? V? No? Yeah, you can, but it will be convenient to use this U for this horizontal axis, right? Because we are interested in this U. So I'm going to make PU diagram. And how does this PU diagram look like? Like this one? No, it is the upside down of this temperature diagram. So at this time, this is going to look like this. to complete this PU diagram, we need to find how many? 3 properties. This one, on the vertical axis, P set saturation pressure. And another one here, UF, the specific internal energy of saturated liquid. And the last one, UG, the specific internal energy of saturated vapor. Then where can you find P set, UF, UG? From this temperature, saturated water temperature table, that is table A2. Here is table A2. Properties of saturated water temperature table. So what is the temperature? 70. So let's find 70. 0.01, 4, 5, 6, 8, 10. Where is 70? Oh, it's not here. The next page. 50, 55, 60, and 70. There's a 70, right? So at 70 degrees Celsius, we need to determine P set, this one, and UF, this one is UF, this one, UG, this one is UG, this one. So these 3 values. And let's look at the unit. What is the unit of this pressure? Bar. And we want kilopascal. 1 bar is 100 kilopascal, so 0.3 bar is 31.19 kilopascal. So let me write this value, 31.19 on this P set, 31.19 kilopascal. What about UF? 292.95. 292.95 cubic meters per kilogram. UG, 2469.6. 2469.6 cubic meters per kilogram. Now, on this PU diagram, this line represents number 1, compressed liquid. This point, number 2, saturated liquid. This line represents number 3, saturated mixture. This point represents number 4, saturated vapor. This line represents number 5, superheat vapor. Now, we made this PU diagram at this temperature. So we only used 70 degrees Celsius. And we have, that means that as long as the water is at 70 degrees Celsius, that water should be on this line. So let's find where is it? Let's catch this one. So U is 500. Where is U? This horizontal axis is U. So where is 500? UF is only 292. UG is 2400. So 500 should be between these 2 numbers. So this 500 is not 50.1. There's no, not here. So this 500 is somewhere between UF and UG. So where is our system? This point. So what is the phase change process? Number 7, right? No, 3. So what is number 3? Saturated mixture. So from here, you can say, oh, this temperature, this U, we have phase change process number 3, saturated mixture. So presently, it is boiling. You have a liquid and vapor together in the system. Yes. Oh, my mistake. You're right. You're right. Oh, that's my mistake. So this one is kilojoule per kilogram. Kilojoule per kilogram. My bad. You want one more problem? Yes. If you want to make TU diagram, you need to know the pressure. And here, we don't know the pressure of the water. So the only property diagram you can make is P something, because you only know temperature. If you know pressure, you can make temperature U, TU. If you know pressure, you can make temperature U. If you know temperature, you can make PU. If you know both temperature and pressure, you can make both of them. But don't make both of them, just one. You want me to go over one more example? Or this is good enough? Yeah. So now, making a property diagram and finding your system, you can do that. Of course, later, I have more than 5 practice problems, so we will go over them. This is just an introduction. I will solve as many problems as I can, because the solving a problem together, that's how we study, right? The best way we study. You remember that? Did I tell you? No. When you wake up in the morning, try to solve a problem. When you clean your teeth, try to solve a problem. When you drive, don't solve a problem, right? That's how I did. 4.0 throughout to PhD. So always keep solving problems. Then we just studied a property diagram. So let's review a few more the things. This one T set and P set. T set is the saturation temperature, boiling temperature. P set is saturation pressure. So at the given temperature and pressure, when you reach T set or P set, you assume that phase change occurs. So let's talk about this P set and P set. Saturation temperature. The temperature at which a pure substance changes phase at a given pressure. So this table A and 3.2 shows the saturation temperature at the given pressure. So this one is T set at the given pressure. So at room pressure, like the atmospheric pressure, 1 atm, approximately 101.325, which is 33. So T set is going to be 100 degrees Celsius. That's what we understand. The boiling temperature of water is 100 degrees Celsius because we live in Mount Pleasant, not Denver, Colorado. But if you go to Denver, Colorado, approximately 2000, atmospheric pressure is only about 80 kilopascal. So what is the boiling temperature? 93 degrees Celsius. So this is the temperature water boils there. So if you cook noodle there, it's going to be undercooked. That's why people use what is called pressure cooker, trying to increase the atmospheric pressure so you can increase the boiling temperature. What about Mountain Everest? How tall is Mountain Everest? 8,845 presently. When I was, the undergraduate students, at the time, the height of Mount Pleasant was 8843. So these days, there's 2 meters, the snow on top of it. So the atmospheric pressure is this low. So the boiling temperature is only 66. So when you, take an airplane, sometimes, they serve food. Are they tasty? No. Why is that? because their water boiling temperature is lower than what we do, here. Of course, the food being cooked in the airplane, maybe less taste. Think about, the cooking a noodle. If it is, some instruction says that you need to cook it, in a boiling water for 20 minutes. So if you cook 20 minutes in Mount Pleasant, it's going to be completely cooked. But in an airplane, let's say, what is the altitude, the elevation of airplane? Pretty high. So if you cook there, to give the same amount of heat for the food, you may need to cook 40 minutes or 50 minutes. So imagine that your noodle is being cooked for 40 minutes in water. You think that it's going to be tasty? Not really. That's why if you eat, the food in airplane, it's not tasty. Then why they don't, pressurize the cabin to meet this atmospheric pressure? Because it costs a lot of fuel. So they maintain somewhere here. So what about, the P set? At 20 degrees Celsius, that's the room temperature in this classroom. What is P set? 2.34 kilopascal. That means if you have water here, and then you decrease the pressure of the air in this classroom down to 2.34, you will see water boils at 20 degrees Celsius. That's what P set means, okay? Then, before we go forward, let's learn one more thing, that is enthalpy. Enthalpy is H. This enthalpy is a combination property. That means that, when you add this U, by the way, this U is what? Internal energy, right? What is PV? Do you remember PV? We studied PV in chapter 2. I told you that this is the flow energy. So when you combine internal energy and flow energy, that is enthalpy. That's it. There's no special meaning of enthalpy. It is just internal energy U plus flow energy PV. Then we can just use U and PV. Why we need to combine that and then, to create another thermodynamic property? Because this U plus PV come together very often in thermodynamics. So more often than U itself or PV. So throughout this semester, you will hear enthalpy more than internal energy U. That's why, we make this enthalpy, even though it has no, the meaning in physics. It's just for your convenience. Okay? So that is H, enthalpy. That's U plus PV. So that's everything. And let's study how to evaluate a property. So whenever you have a phase change material, let's talk about water. One of the most widely used phase change material. If you want to evaluate this water, evaluate a property of this water, step number 1, we need to determine the phase change process. Phase change process number 1, number 2, number 3, number 4, number 5. How do we do that? By using property diagram. What is property diagram? Like PV diagram at the given pressure or PV diagram at the given temperature. They look like this, they look like that. Now you know how to do that, right? So you need to determine the phase change process first before evaluating a property. Then let's assume that you already know the phase change process. There are 5 phase change processes. Number 1, compressed, liquid. Number 2, saturated liquid. Number 3, saturated mixture. Number 4, saturated vapor. Number 5, superheated vapor. So we use different approach to evaluate their property. That's why we need to determine the phase change process first by using a property diagram. Then which one do we want to study first? Let's study the easiest ones. There are 2 easiest ones. Number 2, saturated liquid. Number 4, saturated vapors. If you want to evaluate, let's say, a specific volume of saturated liquid or saturated vapor, how can we find them? We already did in the previous problem, a previous example. The specific volume of saturated liquid, saturated vapor, they are already given. The specific internal energy, U, of saturated liquid, saturated vapor can be found from this table. Enthalpy, HF, Hg can be found from this table. So, it's simple. If you want to find the specific volume of saturated liquid, it is going to be just Vf. Saturated vapor, that's Vg. Where do you find them? From a property table. If it is water, table A2 or table A3, table A2 or table A3. If it is internal energy U, UF, UG. If it is enthalpy H, HF, Hg. So finding the properties of number 2 and number 4, there's no difficulty. You can find them directly from a property table. It just depends on, whether you know temperature or pressure. If you know temperature, table A3, A2. If you know pressure, A3. So number 2 and number 4, they are easy. What about the next one? Number 3, what if you have a saturated mixture? Then there's a problem. What problem? The mixture, saturated mixture is a mixture of saturated liquid and saturated vapor. So you have a liquid and vapor. When you have a liquid and vapor, there can be many different mixtures. Let's say 10% liquid, 90% vapor, or 50% vapor, 50% liquid, 30% liquid, 70% vapor. So depending on the ratio between liquid and vapor, the properties of the mixture should be different. So if you want to evaluate the properties of this saturated mixture, you need to know the mixing ratio first. How much liquid do you have? How much vapor do you have in the mixture? That means we need another parameter that shows the ratio between liquid and vapor. That is called quality X. Quality X is the ratio between liquid and vapor. The mathematical form of this quality X is mass of vapor over mass of liquid plus mass of vapor. So let's say you have only liquid. What is the mass of vapor? 0. So this quality X becomes 0 when you have 100% liquid. When you only have 100% vapor, the mass of liquid is 0, so mv over mv is 1. So if you have only liquid in the mixture, if you only have a saturated liquid, this x becomes 0. So the quality x of saturated liquid is 0. On the other hand, if you have only vapor, there's no liquid, only vapor, saturated vapor, quality x is going to be 1. If the quality x is between 0 and 1, then you have a mixture. This quality x is the ratio between saturated liquid and saturated vapor. So if you have compressed liquid, what is the quality x? There's no quality x. What about a super vapor? What is the quality x of a super vapor? There is no quality x. There is no quality x. There is no quality x. Then if you know the ratio between saturated liquid and saturated vapor, since you know the properties of saturated liquid, the properties of saturated vapor, you can use a linear interpolation to determine the properties of saturated mixture. Then what is that linear interpolation? If you want to determine V, V is Vf plus quality x times Vg minus Vf. This is how you evaluate the specific volume of saturated mixture. What about if you want to determine specific internal energy U? U is Uf plus quality x, Ug minus Uf. What about if you want to determine specific enthalpy H? I don't have to explain again. H is Hf plus quality x, Hg minus Hf. So that's how you evaluate the properties of saturated mixture. Any question? Then 2, 3, 4. Now we have 1 and 5. Which one? 5 first, because 1 is a little bit complicated. If you know you have a super vapor, if it is water, table A4. That's it. Then let's go to table A4. This is table A4. Looks different from A2 and A3. You have many sub-tables inside. So this table is good for pressure 6 kilopascal. This table is good for pressure 35 kilopascal. This table is good for 70 kilopascal. This one is good for 100 kilopascal. So depending on the pressure value of your system, you can find appropriate table inside table A4 and then use the values there. So if you look at the first column, it's temperature. If you know the temperature, you can find specific volume V, specific internal energy U, specific enthalpy H, specific entropy S. Then let's see. Let's to talk about an example. It was always the best to practice rather than just the listening to, right? Let's say I want to determine the internal energy U of water whose pressure is 700 kilopascal, and temperature is 300 degrees Celsius. And let's assume that we already know the phase change process. It is number 5, superheat vapor. Then we know we need to go to table A4 and find a table for 700 kilopascal. If you look at the pressure unit here, it's bar. So 700 kilopascal is 7 bar. Where is the 7 bar? This one. So if you want to determine this U, it's going to be one of these values, right? So this is the table for 700 kilopascal. So what is the temperature? 300. Okay, we just need to find 300. Where is temperature? Here. 180, 200, 240, 280, and 300? No, 320. So there is no 300. If it is 280, internal energy U is going to be, if it is 280, internal energy U is going to be this number, 2766.9. If it is 320, the internal energy U is going to be this number. So if you want to determine U at 300, should we select this one or this one? Or randomly, a value between these two numbers? Maybe I can say 2,800. Is that okay? No. Then what you do? We need to do a linear interpolation to determine U at 300 degrees Celsius. Then the question is, how can we do a linear interpolation? Let me give you an equation. So this is how you do linear interpolation. So we know temperature and U. So T and U. So let's say the left-hand side is temperature T. The right-hand side is specific internal energy U. Okay? Then I'm going to write the lower bound of the temperature and the upper bound of the temperature, 280 and 320, in the denominator of temperature. 280 and 320. 280 and 320. So the bottom left, on the left-hand side, we have 280. The bottom right of the left-hand side, we have 320. Then we know U value at 280 and 320. So I'm going to write these two in the same place on the right-hand side. So what is U at 280? 2766.9. I'm going to write this value on the right-hand side at the same location, bottom left, bottom left. So here we have 2766.9. 2766.9. What about 320? This is U value at 320. 2831.3. 2831.3 at 320. So once you write the lower bound and the upper bound of each side, temperature and U. Now, what is the temperature that we want to evaluate U? 300. So I'm going to write 300 here, 300. Top left on the left-hand side. And the unknown U at 300 should be the same location on the right-hand side, top left of the right-hand side. So this is the unknown U. If you solve this equation, you get U at 300. But this equation is not complete because we don't know the number here. We don't know the number here. Then you can write the number below. The 320 just got promoted, so 320. 2831, 2831.3. And if you solve this equation, you get the specific internal energy U at 300. That's how you do linear interpolation. What about if you want to evaluate U at 600 kilopascal? Do we have 600? No, there's a 500, there's 700. Then you can do a linear interpolation between these two. What about if you want to evaluate U at 600 kilopascal, 300 degrees Celsius? Then you need to do a linear interpolation between these two and between these two points. Okay? Any question about linear interpolation? In your homework assignment, you may see some linear interpolation, so you can practice, right? But in your exam, I will do my best to minimize the number of linear interpolations because you're working on a limited time, okay? So that's how you determine a property of saturated and superheated vapor, table A4. Then that's not it. One is missing. Number one, compressed liquid. We study number one at last because this one is a little bit complicated. Then the first question you may ask is going to be, okay, so there's a table 2 and 3 for 2, 3, 4. Table A4 for number 5. Isn't there a table for compressed liquid? Yes, there is. Yes, there is. Then can we just use that table? Or it depends. So let's go to table for compressed liquid. That is 2, 3, 4, and which table? 5. So let's go to table A5. Properties of compressed liquid water. And when you look at this one, you will be surprised. So one thing that you can notice here is this table looks very similar to those of superheat vapor. So using this table should be the same as superheat vapor. Yes, you're right. But there's one problem. What is the lowest pressure? 2.5 megapascal. That is 25 times greater than the atmospheric pressure. So if you want to use this table, the minimum pressure is going to be 2.5 megapascal. 5 megapascal, 2.5 megapascal, 5, 7.5, 10, getting worse and worse, right? What about if you have a compressed liquid whose pressure is less than this value? Then can you use this table? No. Then why there is no table for lower pressure than 2.5 megapascal? The answer is simple, because it's not necessary. When pressure is not that high, the effect of pressure on your compressed liquid is negligible. So we don't need a table. What do you mean, negligible? Is there any property table that we can use for a liquid? Yeah. What table? This is not the only liquid. There's a liquid. Saturate the liquid. So why don't we have a table for low pressure? At low pressure, we assume that there is no difference between these two. Then pressure doesn't affect the properties of compressed liquid. Then what property affects the property other than pressure? Temperature. So as long as the temperature is constant, there is no difference between saturated liquid and compressed liquid when pressure is not that high. So what was the minimum pressure in the table? 2.5 megapascal. So that's the magic number. When pressure is greater than or equal to 2.5 megapascal, there's nothing we can do. Go to the table A5. But if pressure is less than 2.5 megapascal, then we assume that there is no difference between saturated liquid and compressed liquid, as long as temperature is the same. So that means if you want to determine specific volume V, oh, don't worry about that. It's going to be Vf, because that is the specific volume of saturated liquid. But at the same temperature, T, what about, the specific internal energy U? No problem. U is the same as UF, saturated liquid, as long as temperature is the same. What about H? H is the same as HF at the same temperature T. So this is how you evaluate a property of phase change material. So step number 1, use a property diagram to determine the phase change process. Then step number 2, use these rules to evaluate the property. So this one slide, one page, shows everything about finding a property. And about 40% of the first exam is about this slide. Isn't that nice? You already know 40% of your first exam. And what do you mean? The 40%. There is a practice. There's a problem that we're going to go over. That is this one. It's called a table problem. So, what time is it? 5 minutes. So let me explain how you can play this table. The first, each row represents one problem, one independent problem. So we have a temperature, pressure, H, specific enthalpy, X, quality X, and phase change process. This row, this table give you two values. In this case, we have a water whose pressure is 200 kilopascal, quality X is 0.7. We don't know anything else. So find T, find H, find the phase. Or the second problem, I don't know anything about this water, but temperature 140 and specific enthalpy 1800. Please find P. Please find X and the phase. So how many problems? 5. You will see a similar table in your first exam, that is 40%. That means you need to practice how to evaluate a property based on this slide. Yeah, not today because we are running out of time. This coming Tuesday. I think we can complete this table this Tuesday. If we can, our first exam is going to be the following Tuesday. If we cannot finish by Tuesday, we can finish it by Thursday. Then our first exam is going to be a week from that Thursday, so the following Thursday. So I think I already told you. The first exam